Well, it's time. Welcome back, everyone. We're just about to close out week number one, so happy Thursday. And kind of the mind-blowing thing about an accelerated 8-week summer class is that once we complete week two, a week away from today, we're already 25% done with the entire semester, so it goes pretty quick. So far for the announcements, I don't have too much to say other than assignments 2.2 is due today. I'll do the grading first thing on Friday morning. The next assignments, these are going to be due next week to give just a little bit of breather room, so not everything is due at once. And currently we're in section 2.5 on continuity. Here's our given definition to the right on example one. But any questions or comments whatsoever before we get started? Okay, well, let's begin. So we left off looking into continuity, defining it, and looking at some conceptual graphs on working through it. We split example one in half. Usually I'll try to avoid that, but it seemed to just make sense last class. For the refresher, here is our definition on what we mean by continuity. The limit of f of x as x tends towards a is f at a. When we look at that compound statement, it's good to just kind of pause and think through it. What this is trying to say altogether is as the input value gets closer and closer to a, the output f at x will get closer and closer to f at a. And you can make the outputs as close to f at a as you would like by making x sufficiently close to a. So whenever this limit occurs, we also said that this is essentially just direct substitution. We threw in a for x, and that's the output to the limit. When this happens, we say that the function f is continuous at a. So that's our core definition. We looked at single-sided continuity, so we're going to review that as we work through example one. Also, it's nice to see it through the analytical definition. Here it is just on the ordinary notes, same exact definition. But it's good to know in our mind's eye, on our mental chalkboard, what does continuity look like? It means a nice unbroken curve. There's no holes, no vertical asymptotes, no jump discontinuities, for example. And so this curve is continuous everywhere except at -4. At -4, the function value is 1, but the limit as we tend towards -4 on both sides is 2. And so we don't have that equality right there. The limit is not equal to the function value. So this means it's discontinuous, and that's one way that can happen on a graph. So that's the review on double-sided continuity. Single-sided continuity has these features going on. We're still trying to make the equality come out here or right here. We have equality with the limit and the function value. For a right-sided limit, we say it's continuous from the right. If equality occurs on a left-side limit, we say it's continuous from the left. But the refresher here is, it's kind of easier to spot just on a graph. Continuous from the left by what this information is saying is, if we move through the curve going from left to right, landing on a solid dot, that's the critical part there, you have continuity from the left. We go from right to left and we land on a solid dot, we call that continuity from the right. And again, continuity from the right on this one, because the right-hand sided limit agrees with the function value. So it took a while to talk through that, to draw it all out. Any questions or comments at all, folks, about the refresher so far? Okay, and then here's the example that we cut in half before we ended class on Wednesday. We looked at just another pathological looking function that has several discontinuities, 4 in total. We classified them as well. And in the homework, when it asks you to list discontinuities and explain why it's discontinuous, you're really just saying this, that discontinuous at certain points because it's either removable, or it's a jump discontinuity, or it's an infinite discontinuity. Removable means there's a hole in the graph, maybe undefined or defined in a weird way. There's just a hole right there. Jump means a curve either goes up or down and then continues on. And an infinite discontinuity just means vertical asymptote. So that takes us to our part B. For each of these four discontinuities that we labeled and categorized last class, we just want to determine if f is continuous from the right. Let me keep those colors the same. Okay, blue is the right and green is going to be the left. So we're just determining does single-sided continuity exist from the right or from the left at each one of those four different discontinuities. This is kind of tricky in its way until we discuss how this goes. If we look at, say, 1 and 2, well, it didn't look like the last graph we discussed when we discussed continuity just from the left, continuity just from the right. When it comes to removable discontinuities, these are always neither. So at x equals 1, x equals 2, these are, let me try again with the curly brace, neither continuous. I'll use CONT for a shorthand on continuous from the left or right. To get continuity on a single side, it cannot be removable. At the same token, vertical asymptotes just completely eliminate the possibility of continuity from the left or the right, at least unless one curve actually ended on a solid dot. But that would have to be very apparent. It would have to be written like this. If we had a solid dot here, we would say this one's continuous from the left. But in the absence of a solid dot, we're interpreting this curve as just going up and up without bound on either side of the vertical asymptote at x equals 5. So we'll also say at x equals 5, neither as well, short for neither continuous from the left or the right. Finally, there's only one discontinuity left, x equals 4. But when we look at x equals 4, we come in from the right-hand side, we land on an open circle, so there is no continuity from the right. But if we approach 4 and we're coming in from the left-hand side, we do hit a solid dot, and so that's the one point of single-sided continuity. Right there, we can say x equals 4 is continuous from the left. So that's the wrap up of this one. Really just kind of nice to split this problem in half, gave us a chance to refresh this as we start class today and think about single-sided continuity again after a fresh start. Any questions or comments at all after getting through this one? Okay, well, so far these are the major concepts, the new types of terminologies we're going to look at: continuity, either double-sided or the single-sided continuities. What we're going to do next is expand a little bit on this, creating our own graphs, say on example 2, and then categorizing the kind of functions that are continuous. So that's this long list of theorems here. We'll practice on the example below. After we do that, we'll practice taking limits, but this is going to be kind of the fun part we hinted at on last class. These limits go really fast because we're just going to use continuity. So to start off, here's kind of the challenge question. We looked at several graphs already in these notes, but now we're doing this in reverse. We're constructing our own graph that has to satisfy all 5 bullet points here, all 5 conditions simultaneously. One single function, which means it has to pass the vertical line test as well. So the function is going to be defined on R. We're just stating its domain is all real numbers. So if you see that fancy, sometimes called a chalkboard bold R, it just means the entire number line from negative infinity to infinity. So all points on this curve have to be defined. So that's one condition we'll just have to come back to make sure we don't have any undefined points whatsoever on our graph. Let's just use all of our white space this time. We might as well. Next bullet point condition says that the function is continuous only from the left at x equals -1. So let's drop a value -1 here. Continuous only from the left. When you see single-sided continuity, each and every time this comes up, a good way for drawing the graph is use a jump discontinuity. I'll use DISC. Well, that's kind of a bad shorthand. Let's just spell it out. Discontinuity. That's a better shorthand. I'll use DISCONT dot for a shorthand on discontinuity. So if we want to jump discontinuity, that means there's going to be a couple open circles. Well, let me say that better. There's going to be two circles. One of them is going to be open, the other closed. Now we want to draw a curve going slightly to the left of -1, slightly to the right. We don't want to go too far because there's 3 other bullet point conditions. But it's very critical when we say continuous from the left, how we approach this. We can't make the curve come in from the right-hand side on the solid dot. That would have been continuous from the right. And if I make it come in from the left-hand side onto the solid dot as well at the same time, that's continuous from the left, but it said only from the left can we have continuity. So what we should do on this one is draw a little bit of the curve coming into the right, landing on the open dot. Continuous from the right is now impossible. Draw a little bit of the curve coming into the solid dot. So now if you come in from the left, land on a solid dot, that is continuity from the left. And now only from the left. So that takes care of bullet point 2. 4 more to go. But any questions at the moment? Okay, let's go for bullet point 3. Next condition is that there's a jump discontinuity at -3. And it doesn't specify anything about how single-sided continuity is going to work on this one. So it's up to your imagination how you want to draw that out. Again, this is why we only drew a little bit of the curve, because there's more conditions at -1, -2. There's a new condition rather right at -3. If there's a jump discontinuity, you can be creative and make it look like this. Let me put an open circle, another open circle. Could go like that. Notice -3 is the farthest left point, so we can just let the curve do anything we like, going far to the left. But we do have a problem. The jump discontinuity is just fine. But if we look at all of our conditions we see so far, there's still one problem at -3. It's because of that bullet point right here. The function has to be defined on R, so all real numbers, but f of -3 is undefined as it sits. You can make one of these dots solid if you like, or you can be creative and make solid dot just somewhere else. It's completely up to you. There's infinitely many correct answers to this kind of problem. As long as there is a value for -3, there it is at this height on the y-axis, we're not violating condition number 1, the first bullet point. All right, so we have our single-sided continuity from the left. We have the jump discontinuity. Now we need a removable discontinuity at 2. So for removable, let's go 1, 2. The idea for removable is it's very close to being continuous, but there is a 1-point problem. We want to put in an open circle right at 2. Make there be a hole in the graph, so say something like this. But now we go back to the first bullet point. We need to have this defined in some way. So put a solid dot somewhere else. So that's what the removable discontinuity would look like. Just one hole in the graph, not a whole jump like what we see here. So that's the removable down. Any questions or comments so far? Okay, last condition, we want continuity only from the right at x equals 5. So let's go 3, 4, 5. When we're looking at single-sided continuity, we make one open circle at any height you'd like, maybe something below the x-axis for just some variation. One is solid dot. Doesn't matter which one is open, which one is solid, but what does matter is if we say continuity from the right, that means as we come in from the right, landing on the solid dot, we have to in fact land on the solid dot. We can't come in from the right and go to the open circle. That would violate the continuity from the right. So if we do something, say, like this, give the curve a little bit of character, just make sure it does pass the vertical line test is the only requirement. Then we're not completely done because this part of the curve has to come in and hit the open circle there. So that's what continuity only from the right would look like. And now a quick scan. If you imagine a vertical line, say this one, going through the graph from left to right, it has to intersect the graph at exactly one point everywhere because the function is defined on R and it has to be a graph of a function past the vertical line test. So as we scan this line through, everywhere on the graph, it does hit a point. Hits it exactly once. Imagine that we drew that completely vertical. We might have to use our imagination on some of these. If that's the case, we're all set, and we've completed condition 1, and we in fact have a function 2, passing the vertical line test. So that's the review on pretty much everything we've done so far up to this point in the notes. Any questions whatsoever, folks, with continuity or this graph problem in particular? Okay, now we've seen the conceptual side of continuity, visualizing the technical definition through the lens of graphs, which is a great way to internalize this. Now, just like we did with limits, we're going to turn this over into the analytical side. We want to use continuity for the major purpose of computing limits. So the big thing we need to know then is, well, which functions are continuous? If we can answer that question, then we can compute limits in a very, very fast way. The limits that we did in the prior section, 2.3, still have to be done in the hard way because all those limits at the very end of the notes, they didn't have continuity until we simplified the function. But these problems, when it says use continuity, means they are continuous functions. So we just have to rationalize why is natural log 9 minus x squared in fact continuous. So that's where all of these supporting theorems come into play. Here, we're going to do an exercise below, but I just call this a non-example. I just launched right into the instructions. My reason for that is I feel like this is an important problem just for the sake of us reading through these theorems, but this doesn't make a very good, say, homework problem or exam question. So think of this exercise we'll do below the red dot there, really for the sake of just a help in reading these definitions, seeing how it works. So let's go through this. First, theorem number 4 is about combining functions. If you have two functions, f and g, and they happen to be continuous at a number a, and c is some other constant, it could be 0, could be 17/3, pi divided by square root of 12, something random like that, just a constant number, not a variable. So grab two functions continuous at a, an arbitrary constant, then every one of these combinations of functions would then become continuous. So it says if you start with a continuous function f, another continuous function g, here there's two signs, but we only picked one really. This is just a shorthand, either f plus g or f minus g, also continuous. So you can combine continuous functions in this way. If you have a continuous function f and you scale it, multiply it by, say, 5, it's still continuous. That's a good one to demonstrate with. If we say take a function that's in fact continuous, y equals sine x, that's a nice unbroken curve. But if you multiply it by, say, 5, you've changed the amplitude. That's what CF is doing. It's still continuous. There's no holes anywhere on this graph. There's no jump discontinuities. If you multiply it by 0 even, well, you collapse it to a line, but still it's completely continuous. So that's what this property is all about. You take two continuous functions, say sine x, y equals cosine x. So there they are, both in their full glory, but you decide to multiply them together. It's still continuous. So here's sine x times cosine x. Doesn't want to work that way. Let me try again. Sine x times cosine x. That's the new function. The amplitude. Let me make sure that's the right one. Yeah, that's sine x times cosine x. The amplitude is just the same. The period has changed. If you're thinking about trigonometric identities, then this one just becomes a sine function itself. But yeah, it's absolutely still just continuous. If you divide the functions, it's still continuous. Take sine x, divide by cosine x, provided that you're never dividing by 0. If you're looking at this function, it has loads of vertical asymptotes, but that's because it's the tangent function now. Cosine goes to 0 at infinitely many points, pi over 2, negative pi over 2, and any multiples of those, integer multiples. So it only goes wrong on this one, vertical asymptotes everywhere, because the g function, the denominator, goes to 0 at infinitely many spots. But that's what theorem 4 is all about. You can combine already continuous functions in these ways, obtain continuous functions, just making sure you don't divide by 0 at any one point. Any questions at all, folks, with theorem 4? Okay, then theorem 7 is kind of the big one next. It tells us precisely which functions are continuous, but it has an important catch-all. It says the following functions are only continuous in their domains. Caleb says, if g is all real numbers, though, how can it not be 0? Just to double check on your question, g itself is the function whose domain is all real numbers. And let me think about the question. If g is all real numbers, so are you thinking about, say, this problem here where g is the cosine function whose domain is all real numbers? Gotcha. So if g is cosine, its domain is in fact all real numbers. Trouble with cosine, though, is with y equals cosine x, it goes to 0 at infinitely many points, say pi over 2, negative pi over 2. And so it's continuous at those values, absolutely. But if we go to this function, this is really just tangent, sine divided by cosine. Well, let's put them both on. Everywhere cosine goes to 0, say pi over 2, you have a vertical asymptote. And so this overall function is not continuous at, say, pi over 2, only because cosine goes to 0, putting a 0 in this denominator right here. So it's, does that help with answering the question? I'm just not completely sure what you mean by how it cannot be 0. Yeah, that's absolutely correct. As soon as the function is 0 down below, it's discontinuous. If we want to force this continuous, we could change the domain, say negative pi over 2. If I could type that, let me try again. Less x less pi over 2. And now we have a nice domain. This function, which is again just a bona fide tangent function, is continuous from negative pi over 2 to positive pi over 2 because we avoided all the places where the denominator cosine would have gone to 0. It's a really nice function because it's also passes the horizontal line test, so you can invert it. Here's the tangent inverse. The inverse of that function, tangent inverse, is the purple curve, and tangent is now a fully continuous function but only on that domain that we restricted there. And sure, other domains, but that's the typical restriction for arctangent or tangent inverse. Other questions at the moment? Yeah, that's absolutely correct, Caleb. G has to be continuous, and critically, it cannot cross the x-intercept. In other words, that's what makes the zero occur here, violating the continuity. Yeah, no worries for asking questions. Thanks for asking about those. And your intuition is very correct with that last comment. Other questions or comments at the moment? Okay, well, let's take a look next at Theorem 7. On Theorem 7, this one is giving us a whole category, a catalog of functions are continuous on their domains. So here's the emphasis. First grouping of functions that are continuous on their domains are polynomials. But the nice thing about polynomials is polynomials have domain all real numbers. So for an example of polynomial, think y equals x to the power 7 plus x cubed minus 4, just a random 7th degree polynomial for an example. So that one's continuous on its domain. Rational functions, these are continuous on their domains, but their domains are not all real numbers. A rational function could be y equals x plus 3, x over x minus 8. This one has a domain exclusion. You cannot plug 8 inside this function. So it's continuous as long as x is not equal to 8. Everywhere else, it's a rational function. You can use direct substitution, and you have full continuity. And then so on. By root functions, we mean functions, say, along the lines. Y equals, maybe it's the 5th root of x. This one's continuous on its domain. This one has domain all real numbers. Trigonometric functions like sine, cosine, tangent, secant, cosecant, and cotangent, all continuous on their domains. But only sine and cosine have domain all real numbers, like the tangent one we were looking into. Tangent, cotangent, secant, cosecant, they all have exclusions where it's not values not in the domain. But for all of their values in the domain, these functions are continuous. Same for their inverses. And the exponential functions, say y equals 7 power of x, all continuous on their domains. These have domains all real numbers. And last, logarithmic functions, say y equals log base 10, or the natural log if you want base e for the example of x. This one's completely continuous on its domain. Just have to be mindful that the domain of this one for any logarithm is going to be from 0 to infinity. So essentially what this is saying altogether is all of those functions that you've encountered in a pre-calculus 1, pre-calculus 2 for trigonometry course, these were all continuous functions as long as you stayed inside the domain. So that's a nice classification of very, very wonderful continuous functions. Any questions at all, folks, with Theorem 7? Okay, Theorem number 8, we're getting through the list here. This one is a nice property that we're going to cite here and there when we take limits. It says if your outer function f is continuous at a number b, and the limit of g exists and equals b, then you're allowed to take a limit operator, limit as x tends towards a, commute it inside the function, so f stays where it is, this becomes b, and you just get the result f of b altogether. In fact, we've done that in a couple places already in section 2.3. particularly with root functions, square roots. If you have a continuous function, the limit operator can go on the inside. So that's a nice, wonderful property as well. This one is more about function composition, f of g of x. And then theorem 9 just expands on that. If g is continuous at a, f is continuous at g of a, the composition f of g of x, defined in that same way, f of g at x, is also continuous on a. So theorem 8, theorem 9, they're both saying about the same thing. One is just a more mechanical view, showing the limit come inside. And theorem 9 is just a statement of overall continuity. So that's our big tally of theorem 7, category of continuous functions. Theorem 4, algebraic combinations of continuous functions. And the last two theorems telling us that composition of continuous functions are continuous as well. So again, nice full tour of pre-calculus 1 and 2, telling us pretty much everything is continuous. Well, if that's the case, just to illustrate how theorems 4, 7, 8, and 9 go all together, we're going to explain why that is a continuous function on the set of all real numbers. First, any last questions or thoughts before we launch into that explanation below? Okay, there's really two major functions here in a certain sense. There's a function x, much like, say, the f right here. Let me just circle that while we're on that thought. So there's one function, and then there's a function cosine of the square root of x squared plus 1, a big composition of functions. That's like the function g here. So the first thing that's going on is we have two functions being multiplied. We can give them names like f and g if we'd like, but f is already used, so we could give them different names like u and w. Those are completely fine as function names. So we can start off by explaining continuity, first by saying u of x equals x, w of x equals cosine square root x squared plus 1. So there's two functions altogether. And if you can demonstrate that both the function u, the function w are continuous, you just go to theorem 4 and say, we're multiplying them together, so it's therefore continuous. So we just have two more steps to go, show that that's continuous. But that's actually really fast. U is a degree 1 polynomial. So it is continuous. I'll use CONT once again for continuous by theorem 7. So that's what theorem 7 was saying. Polynomials, even if it's just x, that's a degree 1 polynomial, sometimes called a power function. It's continuous on its entire domain, all real numbers. So in a certain sense, we're halfway there. There's not too much more to say, except that there's three functions altogether here that we need to analyze. There's cosine, there is the root function, the square root, there's x squared plus 1, another polynomial function. But when we look at all three of those functions, they're continuous, every single one of them. It's inside theorem 7. So this turns into kind of a big writing problem, but just to see how theorem 7 works, let's write it all out. So let's start first, let's work inside out. The innermost function in this three function composition is x squared plus 1. So we can start by saying x squared plus 1 is continuous on R by theorem 7, since it is a polynomial. It's degree 2, or you could just say it's a quadratic. So we have that once again, polynomial is continuous on its entire domain. So that's a good start. Now the square root symbol we have to be kind of careful of. The square root is going to be continuous as well, but it has a restricted domain. The domain is just from 0 to infinity. However, you can still plug in any real number inside of x squared plus 1 inside that square root symbol. Reason being is it'll never come out negative. The minimum value for x squared plus 1 is 1 itself. So even though the domain is short for the square root symbol, the domain of this entire function is still all real numbers. So let's go off to the next part and say, next, square root x is a root function continuous on 0 to infinity by theorem 7. I'm using TH, just a shorthand for theorem, but I'll usually try to capitalize the T in that shorthand. So root x squared plus 1 is continuous on R. Again, this one's still continuous on all real numbers because the input x can be any real number whatsoever on this entire composition here. So we're off to the next level. We're taking cosine of something that can be any real number. But that's okay because cosine is a trigonometric function. Doesn't matter what number you put inside there, it's accepted as an input. So that's going to finish off the last thought. Finally, cosine x is continuous on R, all real numbers, by theorem 7. And so cosine, let me write it this way, of the square root of x squared plus 1 is continuous on R by theorem 8. If we have a function composition of one function that's continuous on R and another function that's continuous on R, the full entire function composition is also continuous. So we had two functions, u of x, just that one right there, another big function, w of x, that entire block right there, but they're both continuous on the entire real number line. That means going back up to our theorem number 4 right at the top, when we multiply the two functions, they must therefore be continuous. So Caleb says on the homework, do we need to name the theorems? No, you do not. Like we mentioned earlier, we're really only doing this one time, just for the sake of showing how each of these theorems work together when we do a visual inspection on a function like this one. But as far as the homework problems go, we're just going to take a look at what is the function. Well, it's another polynomial. We know it's continuous because we've investigated the theorems. We're doing that work now. The logarithm is also a continuous function, as long as once we plug 2 inside here, we're inside the domain. And so we'll just go at it directly. You don't have to do all the step-by-steps like we're doing this one time. So think of the reason we're doing it this time is primarily just to get a feel for what all these theorems are saying in the first place, because it's a lot to just read through without trying to investigate them really closely first at least once. So this is our once. Other questions so far? Okay, well, here's our overall conclusion. We showed, thinking of f times g, that the two functions here, the first one and the second one, are both continuous. So here's our conclusion. We'll use a little fancy triangle symbol to stand for a shorthand of therefore by the writing above, f of x, which is equal to u of x, times w of x, or we could write out in full if we wanted to, but we analyze components in this way, so we're just renaming them, is continuous on R by theorem 4. So that's the one time theorem 4 comes into play on this one. So it's a lot of tools that we've been given all at once for continuity. What we'll be doing next is putting all these things into practice. But any last thoughts or questions on our run through of just investigating continuity on something like this? Okay, well, now we know what functions are continuous, how we can combine them algebraically, how we can do a composition of them even with theorems 8 and 9 and still have continuity. The major thing to not ever forget, though, is continuity is basically just that right there. So if you're going to use continuity to evaluate a limit, that's what you need, this definition. We want to analyze continuity through the graph. That's important. We want to know what functions are continuous. All these theorems are important. But the instructions say use continuity. The major thing that's really, really important is this tool right here, definition number 1. So that takes us to the last bit of exercises down below. We're going to use continuity to evaluate a limit. And I captured theorem 8 for, I think, one problem here at least is going to be particularly useful for us in dealing with compositions. Well, here's a function. If it says use continuity, it's a fair assumption to think that this function should be continuous at 2. But if we thought through it, like we looked at before, 9 minus x squared, it's a degree 2 polynomial. It's continuous on all real numbers. If we plug 2 inside of there, we would just get 5, which is in the domain of the natural logarithm, and that's also a continuous function. So if we're using continuity to evaluate the limit, here's all that really happens on this kind of problem. You take x is 2, let's highlight it in a different way, like in the definition below, substitute it here, and this becomes natural logarithm 9 minus 2 squared. And all we have to do is simplify that down below. So here's what it looks like as a formula where f of x is just any old function. But on paper, when you know the function is natural log 9 minus x squared, it does look a little bit different. But that's the whole punchline. We worked really hard on limits, so this is almost kind of like a vacation based on what we've done before. So that's essentially all direct substitution is. If 2 was not in the domain, then we'd have to work harder, but that's exactly what we were doing in section 2.3. Last thing to do is just simplify it down. This is going to be natural log 9 minus 4 becomes natural log 5, and our work is over right at that spot. Well, we did it, folks. That's probably the fastest limit done analytically this way without a graph all semester. Any questions at all getting through it? Okay, well, let's do it again. This time it's trig functions. And these don't have to work out. It's easy to take a limit where x tends towards something not in domain. That can be problematic. But if we plug pi inside tangent, well, tangent at pi is just 0. That's sine divided by cosine. Sine at pi is 0. And cosine is defined at all real numbers. Cosine and tangent are continuous. And so our work is done. We just have to plug in pi. So running through this one, this turns into cosine tangent at pi by direct substitution using continuity. Again, here's the nice formula down below that we've effectively used. We get this. We do have to evaluate all of our trig functions and give exact values, so there's still one more step to take. Again, tangent at pi just comes out as 0. So this is cosine 0. Cosine 0 comes out as a 1, and our work is done right at that step. So that's 2 down. Any questions at all, folks, running through this one? Okay, we did a little bit of trigonometry on this one. And just for a forewarning on Calculus 1, if you're going into Calculus 2 and even Calculus 3 in the future, trigonometry actually comes up a lot. So we'll be reviewing trigonometry as we go. But if you feel like you just need a kind of a good quick refresher, pull up this file right here, Trigonometry Review. It gives you just about everything, every tool that you're going to need, formulas, identities, definitions, evaluations for purposes of this class and calculus going beyond. Any questions whatsoever on just the trigonometry aspect of this one? Okay, well, looks like one more to go and then another problem down below. On this one, we're taking the limit as x tends towards 2 of arctangent x squared minus 4 divided by 3x squared minus 6x. But using the theorems that we did above on our hard work on that last example, all we have to do is decide are our functions continuous? Arctangent turns out to be a fantastic function. That one's continuous on the entire real number line. Its domain is all real numbers. It has a horizontal asymptote, 2 of them specifically. But nothing goes wrong with the arctangent function. Nice continuous function. On the inside is a rational function. Rational functions are continuous on their domain, but the domain doesn't have to be all real numbers. So we need to do a quick check. If x is 2, is that in the domain of the inner function, the rational one? Just depends if the denominator goes to 0. Take 3 times 2 squared minus 6 times 2. And tragically, that goes to 0, which tells us we have a bit of a hang-up on this one. You cannot use direct substitution. The overall function composition is actually not continuous right at 2. We need to do a little bit more work on this one just to try to get it to simplify down. So this one is a little bit more similar to what we did in section 2.3. But here's another view you can take on this one. The limit of the function on the inside, it actually does exist. It comes out to some number, and whatever number it's going to come out as, we'll call it b. It's going to be in the domain of the function f for sure, because our function f is arctangent. Its domain is all real numbers. So if I can show that that limit here in green exists when x tends towards 2, our work is done. But here's the magical property that we've looked at before. If that limit exists, then the limit operator can commute inside the function f, which is the arctangent function. So here's the step I would take using Theorem 8. Finally, it's relevant. This can now be rewritten. If instead of arctangent, you can shorten this to tangent inverse if you prefer. This is tangent inverse of the limit as x tends towards 2 of this rational function. We need to simplify it down, so we're going to start factoring it. X squared minus 4 is a difference of squares, so this is x plus 2 times x minus 2. There's a greatest common factor in the denominator of, looks like we can pull out a 3x, leaving behind x minus 2. Then we're back to section 2.3 at this step. We can do that limit. We have tools that shows us a cancellation like that is allowed. Once you do that cancellation, this becomes tangent inverse. Limit x tends towards 2 of x plus 2 over 3x. And then continuity takes over right at this step. So we just had to do a limit as we did section 2.3 strategy to get to the point at which we have a continuous function That's rational. You can plug in 2 inside for x. 2 is in the domain of that brand new function right there where the red dot is. And then it's just going to be tangent inverse of whatever the value happens to be. This all worked only because the outer function f, which is tangent inverse or arctangent, was continuous. So this then becomes tangent inverse of, throw in 2 here by direct substitution. So that's going to be 2 plus 2, 3 times 2, just showing that extra step to emphasize the direct substitution. And then finally, this becomes tangent inverse of 4 over 6. It simplifies. Let's keep going, which is tangent inverse of 2/3. It's a strange irrational number. I don't think there's any nice way to evaluate this. And so it's just fine just the way it sits as a exact form tangent inverse 2/3. Well, part C was tricky because we couldn't just plug the number in. And really, the whole purpose of part C is to show how theorem 8 can be used out in the wild in practice for something like this kind of problem. Well, unless thoughts or comments at all, folks, getting through these problems? Okay, well, it turns out I have just one more problem on these set of notes. So let's look at the final exercise, and then we'll move on to the section 2.6, limits at infinity. So this one came with a kind of a forewarning that this is a problem that sometimes can be an unfair one if you didn't expect it. So we're throwing out the fair warning right now. This is a common problem that can occur both on exam 1 and on the final exam. It's a very, very common problem. And the reason is the theme of what we study in calculus is in 3 branches: continuity, differentiability, and integrability. And so this is a direct question to test our understanding of what is continuity. And the bigger punchline in calculus is all those interesting things: continuity, differentiability, integrability. Those 3 things are all defined in terms of some kind of limit. And so that's the major reason that this is a common exam problem, both on exam 1 and the final. So watch out for this one. This is a good one to take down, be prepared for. It starts off with just this information. A function f is continuous at a number -7. Write an equation, so there has to be equality somewhere, that expresses this information using a limit. So to get started on this one, we know that there has to be a limit, so it doesn't hurt to just write that down. If we say continuous at 7, that means that's where x is heading towards. X is heading towards 7 itself. We're talking about continuity of a function f, and when you write a limit operator, this becomes mathematically grammatical when you feed it a function, either using f of x or putting in a specific function like natural log 9 minus x squared, for example. But here it was just f, so we put in f of x. Then we're not done because we have to write a full-on equation that implies there's equality somewhere. And this is finally the big punchline to continuity. The function f is continuous at x equals -7 if, when we go to take the limit as x tends towards 7, it becomes f at 7. So it's a really fast problem. If you know to expect it, it's not too big of a deal to get through. It's an unfair question if you didn't know it was coming. It's kind of right out of left field otherwise. So watch out for something like this. Really, the only thing I can change much is the number right there. Well, the whole section 2.5 really just started from this, and here's how it ends, just using this as a fast concept style of question. We have one more category of limits we want to take a look into, and then finally we're going to wrap back to the start of course, get back into tangent lines, and see how all this machinery we've been looking at, continuity included, helps us to find the slope of the tangent line from day 1 of the class. Any questions at all, folks, then, before we turn to the next section? Okay, let's open up that section. I took a little bit more time this week getting through all the sections that I listed out here than I thought I would take, but that's okay. I think we've been going at a pretty reasonable pace. What's going to happen as you come back to class next week, you'll see sometimes things kind of move around. This section should really be in the next week because that's the week we're going to finish it. I'm not going to try to race through it twice as fast just because we are shorter on time. Also move the due date over by a day as well, so we have the same amount of time on all the other things in terms of class meetings. So we're now in section 2.6. As far as 2.6 goes, these are different kinds of limits. They come back when we're in chapter 4, applications of the derivative with L'Hopital's rule. Really, it's all about horizontal asymptotes. But if you know you're taking calculus 2, the skills you learn here in section 2.6 come back massively in one infamous chapter, chapter 11, which deals with Taylor series, Maclaurin series, power series, and so on. We use a lot of the ideas right out of this section. So this is extending a little bit further on limits than what we really needed for tangent line equations, but it does come back in this course and in the very next one as well. So let's open it up. We start off with two more interesting looking limits. They're both essentially the same, except for one difference. One is a limit as x tends towards infinity, and another one is a limit as x tends towards negative infinity. So very similar limits aside from those two different changes. On the first one, if we're taking a limit as x tends towards infinity for a function f, that means the domain has to include infinity on the right-hand side and just some other number a to start it off. So it has to have no upper bound on its domain. Likewise, if we're doing a limit as x goes to negative infinity, no lower bound on its domain there. So here's the overall definition. Thing to keep in mind is we have never put an infinity on x. Every limit we studied was x heading towards a finite number. Sometimes the output was infinity. Those limits didn't exist, but that was a way in which it failed. And so this is something very, very new when we say x goes to infinity. X going to infinity or x going to negative infinity is really the same kind of concept as a horizontal asymptote. So we will review that as well as we go along. So if the limit comes out as L on either one of these, all that means is f of x gets closer and closer. It could be made arbitrarily close to that number L by taking x sufficiently large. Well, it's heading off towards infinity, so that's what we mean by sufficiently large. If this limit exists, as if we go towards negative infinity for f of x, and we have a value L, some finite number there, that means f of x can be made arbitrarily close to L. As f of x values get as close to L as you would like by making x be sufficiently large negative, like say negative a million, negative 10 power 9, negative 10 power 20, and so on. So those are the two brand new limits. It carries over some of the same kind of concepts, but the visualization of what they actually look like is truly a little bit different. So we'll draw out a couple graphs to show what is going on in spirit with both of these new limits. Caleb says, is Euler's number an example of this? Yeah, absolutely. Euler's number comes up in a limiting process of a particular expression when you have something with, say, 1 over 1 plus n to the power of n. Euler's number comes up, and that is absolutely one of these kind of limits, the first kind right up here. Other questions so far? Okay, again, thanks for that connection. That's a great way to think about these kind of limits just through the definition of Euler's number. I believe that comes up somewhere in the reading in this textbook as well, the definition of that Euler's number, the number E approximately 2.71 and some change, irrational, just like say pi. So let's look into a couple graphs to get the feel for what both of these limits are saying. On my first graph, I want to extend it to the far right because we're taking a limit as x tends towards infinity. Well, let's suppose the graph of this function looks like this. At height 3, there's a horizontal asymptote. For vertical asymptotes, we make it x equals a number. Horizontal asymptotes are just y equals some constant. So this will be y equals 3 is the equation of that asymptote. My function could start here and then go up, maybe cross the asymptote, and then just approach it in this kind of way. I'm imagining the curve y equals f of x is getting closer and closer to the height y equals 3. That means the limit as x tends towards infinity of f of x is 3 for that particular function drawn. And we're going to look at a lot of different kinds of examples where these horizontal asymptotes occur. So that's the first one. Essentially, once again, if we say a limit at infinity, we're just meaning x is either going to positive infinity or negative infinity. You can put a finite number down. That means there's a horizontal asymptote. The answer here is just infinity. The limit didn't exist, and there's no horizontal asymptote whatsoever. Well, at least not in that direction, towards the right. So if we reverse the picture, imagine this whole thing flips around, it would look about like this. I guess we can make the function a little bit different as well. Let's make that horizontal asymptote negative just because we can, that's allowed. So this time I have a horizontal asymptote at height -1. And the function could be really bizarre out here. It can do all sorts of things. It can have removable discontinuities. It could have, say, vertical asymptotes. Maybe strange vertical asymptotes where they kind of split around like this, going in different directions. But if we have a horizontal asymptote to the left, eventually this function has to get tamed, and it's going to eventually do this. It might be really, really far to the left. So these numbers could be very, very large negative. We didn't say what the scale was. I guess we kind of did. That's meant to be 1. But if we are approaching that height eventually for very large negative x, the height is the horizontal asymptote, y equals -1, then that means the limit as x tends towards negative infinity of f of x is exactly the height of that horizontal asymptote, -1. So those are the two new limits. After this, we've rounded up all of our work on studying limits until we revisit it again in chapter 4 on L'Hopital's rule. But any last questions or thoughts at all, folks, with these two new technical limits and their graphs? Okay, well, the next part of the notes is kind of a pre-calculus algebra refresher. There's a lot of functions that just seem to come up over and over again, particularly in a calculus class, calculus 1 through 3. Not having a good mental image of what these functions look like make doing certain limits, like say this one or this one, a lot harder than they're meant to be. So these graphs we're going to take a look at, they're fundamental to calculus 1, major tools in say chapter 11 in calculus 2, still used in calculus 3. And here's the listing of those kind of functions. Tangent inverse, we already visited once. E to the x and particular exponential and all other ones. The, let's see, natural logarithm of x. And I guess that's my list. If for some reason I thought I had a bunch more, but this is a good roundup of common functions we need to have a good mental image for just to do the limit. Logan says, so it can be the limit since it crosses at some point, but it gets closer and closer, the larger the numbers become. Yeah, absolutely. In fact, the curve could cross infinitely many times, as weird as that sounds. But as if you go further and further to the left or further and further to the right, if it eventually approaches a number, then the limit exists. And just to go along with that comment there, let's put down a really bizarre function. Let's let this one be f of x equals cosine x. Doesn't look too bizarre when you take a look at it, but we can manipulate this function in a lot of weird ways. Let's say we add 1 to that. And let's say we also multiply this whole thing by an exponential function, e to the power of, say, negative 0.5. Or how about negative 3? That's too abrupt. How about negative 2? Something like that. So this curve, actually I want to put this slightly different. Sorry, kind of debating myself how I want to present this curve. I want that +1 out here. I want to put my exponential out in front. So as it stands, this function that we're plotting, it has no limit at infinity. And that's because it's going to oscillate up and down infinitely many times forever. Let's extend this x-axis just to really emphasize that. Let's go off to, let's say, 2 pi times 10. So 10 periods of the function. Let's plot another curve, y equals 1. If we change the function f of x in a kind of a dramatic way, the horizontal asymptote will be 1, and the limit as x goes to infinity, it will be 1 as well. And here's the function I had in mind. Let's put in an exponential, e to the power of negative x. That's kind of brought to negative 0.5x. That'll do it. Let's go with negative 0.05x. So if we put in kind of a bizarre damping factor right there, multiplying cosine, and cosine starts off looking normal, but as x gets bigger and bigger, that factor gets closer and closer to 0. And so the amplitudes just start to damp out. They get smaller and smaller, and they all approach height 1. That means for this particular bizarre curve, the limit as x tends towards infinity of f of x is actually 1. And it's going to cross that curve infinitely many times. No ending to how many times it crosses. But after every single cross, it gets closer to the curve every single time. And we can get as close to that curve as we want just by taking x sufficiently large. So this is another kind of a pathological looking example of what can happen for these kind of limits. Other questions or comments or questions about this particular example? Okay, let's throw this on here on the notes just for another take on some of these new concepts we're taking a look at. Now next, let me get that out of there. Now next, what we're going to take a look into is what's going on with some of these particular graphs. These are some common graphs that seem to come back over and over again in a lot of surprising contexts in the courses, like we mentioned. Here's our kind of review on what we were hinting at with the prior definitions. If you take a limit as x goes to either infinity or negative infinity, and the limit exists as some finite number, then y equals L is a horizontal asymptote. So the logic goes both ways. If this limit exists, you have a horizontal asymptote. And if you have a horizontal asymptote, one of the limits must exist, or maybe both of them at the same time. So let's turn that around, take another look at a new curve, y equals tangent inverse x. So for this one, the ultimate thing we want to evaluate are these limits. These are the things that can come out of the blue in both calculus 1, 2, and 3. But to do these limits, as x goes to negative infinity or positive infinity, Part A is really the mental image of what we need to know. So if this is kind of foggy information, if it's been a little while, this might be information that you would want to include on your 1 page of notes that's allowed on any exam in this course. The graph for y equals tangent inverse x goes like this. It does intersect right at the origin, so tangent inverse 0 is in fact 0. But aside from that, the other features of this graph is that it has horizontal asymptotes. One at height, exactly pi over 2, and another one at height, y equals negative pi over 2. Now, if we plot the entire curve, here's what it would look like. Comes around through that point there. It never reaches the height pi over 2. It never reaches the height negative pi over 2 either. However, this is enough information to inform us that these two limits here and here both exist, because it gets as close to pi over 2 as you would like, because that is a bona fide horizontal asymptote. So here's the rundown for this one. The way to analyze these limits is first look which direction you're going. If it says limit as x goes to negative infinity, that means you're concerned with this end of the graph. What happens when the x values are large negative? They're getting lower and lower at every step, but there's a lower bound. It never reaches negative pi over 2. We just get as close to it as we'd like by going further and further to the left on the curve. That means the limit exists as a negative pi over 2. But really, it's just the horizontal asymptote. Notice we need to know the direction we're going on x to pick the right horizontal asymptote, because there's two on this graph. So these problems, again, can be kind of tricky because that's the whole punchline. We didn't do anything fancy on evaluating this limit with continuity. We didn't do any kind of algebra on this. We just had to know the fundamental features of the graph of tangent inverse x. So pretty weird limits in a certain sense. We're just using the fact we know horizontal asymptotes exist. Any questions at all, folks, on getting through that first part here? Okay, well, we'll be doing plenty of examples where we really do have to break out some algebra to see how it goes. The rational functions review material on the Moodle webpage is going to be pretty useful, so this might be a good one to pull out for this section notes 2.6. Now for the last part, if the limit is as x tends towards positive infinity, that means you're looking at this end of the curve. X is getting large positive. It approaches the height of the horizontal asymptote pi over 2, and that means our work is just immediately done making that observation. The limit as x tends towards infinity is pi over 2, and our work is done. Strange limits, interesting process of evaluating them this time. Any last questions or thoughts before we try a different one? Okay, well, let's try this out again. Here's the new function, y equals e to the x. We're going to do the same kind of process. Evaluates the limits purely just based off the knowledge we know about the graph of that function. So we're doing two limits, negative infinity, positive infinity. This time it's an exponential, so the graph is going to look like this. This one intersects right at positive 1 on the y-axis. In fact, does have a horizontal asymptote. The equation of that horizontal asymptote is y equals 0. Algebraic fact about e to the x is e to the x is always strictly positive. You can never even hit 0. It certainly never becomes negative, but it approaches 0 towards the left. So the rough sketch of this curve might look something like this. That's kind of a hard one to sketch. I made my axis kind of long. It's very close to zero if you're way out here, then increases slowly, and then explodes when you go past +1. It starts growing exponentially beyond here. So here's the curve for y equals e to the x. I guess it's already labeled there. Using that knowledge, we have two limits we can evaluate. But again, the direction is really critical on this one. We're going towards negative infinity. That means we're looking at that direction. The height of that curve is getting closer and closer to the height of zero. That means the limit is zero just automatically on that one. And just think how challenging that problem can be if you didn't have the mental image right above. A problem like this can show up in this way. Just give us the value to the limit. So when you see something out in the wild, say in a calculus 1, 2, or 3 exam or homework set, what you want to think about is what is the graph to e to the x? So you can use that information, the horizontal asymptote, to evaluate the limit. So that's one down. But notice that limit is different. X is tending towards positive infinity means we're looking at this end of the graph. It's very different because although there's a horizontal asymptote, that asymptote is only relevant if you're heading towards the left-hand side. If you go towards the right, this one's growing without bound. That limit doesn't exist, but we must put down a symbol. In this context, where the limit didn't exist, but it's growing without bound, we need to put in infinity here to capture that reason the limit failed to exist. So only one limit existed in this case. That's this one for the horizontal asymptote. What we did, folks, that's the exponential function. Same kind of property for any other base, but base e happens to be an important one. We'll see reasons why later on in calculus, why we're like base e. We invert the exponential function. Its functional inverse is the natural logarithm of x. By natural log x, we just mean log base e of x is natural log x. That always looked weird to me. ln for natural logarithm. It's logarithm natural is the way they would say it in French, using the French pronunciation, the reason why it seems backwards. So if we were to graph this one, it's really not too bad. You just have to invert this curve across the line, y equals x, because they're inverses to each other. Here's what this one would look like. Inverse functions means everything flips around, domain and range. A horizontal asymptote becomes a vertical asymptote. Now at x equals 0, if you intersected at 1, 0 for coordinates, you just flip those around and intersect. Well, let me say that better. If you intersect here at 0, 1, forgot how to do the ordered pair, then when you go to the inverse function, you flip that around and go to 1, 0. Put down the ordered pairs just for emphasis. And then here's what the natural log curve would look like. Roughly about like that. It's going to grow without bound, just extremely slowly. It's going to approach the y-axis very, very rapidly towards that vertical asymptote. And now armed with that information, here's the last two limits for this algebraic review roundup. First one, if we take the limit as x tends towards positive infinity, we're on this end. But that's tricky, especially when you look at plots of natural logarithms. Plot natural log. And it might almost convey, depending on your axes as well, that there could be a horizontal asymptote, but it's a lie. The further and further you go out, the higher and higher this curve will get. It just takes some doing to get, say, up to 20. I have to really get out there to hit 20, very far on the x-axis. But this is really growing without bound, and so that limit is infinity. Now, next, notice that this one, well, There's no horizontal asymptote here, so we don't have the same kind of limit like x goes to negative infinity. In fact, that's impossible to do that kind of limit. And that's because the domain of the logarithms end right at zero. Zero is not even included in the domain for a logarithm. So we had to take a right-handed limit specifically. And that is really very specific because limit as x tends towards zero of natural log x does not exist at all. You have to take that specific right-sided limit. The reason this limit doesn't exist is in order to get a number for this, you have to approach from the right side of zero, and you have to approach from the left side of zero. That's a double-sided limit, but there's no domain on the left-hand side. So this is just a nonsensical statement altogether. But you know what? That limit also, it doesn't exist, but it fails to exist in one particular way, which we can identify. We take the limit as x goes to zero from the right. X goes to zero plus, limit from the right. It means we're following the curve down this way. So we're interested in this area of the curve, but the curve is just plummeting. It becomes large negative without bound. And so this limit equals negative infinity. And so that completes the work on this one. This one, the limit as x goes to infinity and negative infinity. It doesn't exist, or excuse me, zero from the right on that one. It doesn't exist on either one of these. There's no horizontal asymptote. And this one didn't exist because there's no horizontal asymptote when we go forward on the right-hand side of e to the x. Well, we did it, folks. Once again, that's our big algebraic roundup for these kind of problems. Any last questions or comments as we reviewed these problems before we go to the next concept? Okay, well, we've kind of taken a look at how asymptotes occur, limits at infinity, or when horizontal asymptotes occur. Now to put it all together, we're going to practice this with one big overall kind of review problem. I felt like this is a good one to put in the notes to end out the first week because we looked at lots of different kinds of limits. And so here's our chance to review all of them. Then after that, we'll look into sketching our own graph. And beyond this point, we're nearly done with the notes. We'll just be doing limits now in a purely algebraic way where graphs don't help us out, like in the last problems whatsoever. We have to crank these out and use theorem 5 to our advantage. We'll do this kind of problem when we come back next week on Monday, so we don't try to rush through any of the content. So first, here's our big review problem for example number 4. Let me try to get a good zoom on this so we can see everything nicely. It looks like I have 12 different limits to get through altogether. One strange looking interesting function. I took this as a screenshot from a different textbook, and one thing I kind of prefer whenever I write down any problem on the homework and certainly exams, so I'd always kind of clarify that that should be a solid dot. That wasn't in the printing of that textbook. So let me put that in just after the fact, just to emphasize, to make everything consistent with what we've done so far. So we're looking at several different kinds of limits. Some of these limits are as we head towards a finite number, like limit x tends towards 4. Some of them are single-sided, like -3 from the right here. Others are as we go to infinity or negative infinity. These were the new ones. So let's run through these as kind of a, again, big overall review problem. I think these would be kind of valuable if you took your time, grab some scratch paper, maybe you've already printed out these notes. Take a look at these, solve as many as you can, and then we'll do it again as a class all together, and let's say about 2 minutes from now. So I'll get quiet, let you kind of absorb this, give these a try. Okay, that's been about 2 minutes, a little over 2 minutes. Hope you had a chance to try out some of these. Let's go through them just one at a time, left to right, row by row. For each of these limits that I go to evaluate, I want to highlight what part of the curve I'm looking at as we do each one of these. So to start out, if it says limit as x tends towards 4, that means this is the whole part of the curve that we care about, right around here. And this one's nice. Doesn't look like there's any tricks. It's in fact continuous around 4. As we get closer and closer to 4, the height of this curve gets closer and closer to 2. So the output to this limit would just then be 2 altogether. So that's 1 down, about 11 more to go. And really that's kind of the process. Look at where x is going first. Find that region along the x-axis that matters. This one is we're going to 2 from the right. We're going towards positive 2 from the right. The only region that really matters is something like this. This is the part of the curve I care about. X has to be strictly larger than 2. We want to be nearby 2. So as the x coordinate heads towards 2, we're just going down, 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 getting closer and closer to a height of -3. The output to the limit is that y-axis value that we're approaching. And so this one would output a -3 altogether. So that's pretty much the name of the game. Find out where x goes, find out what coordinate we're heading towards, if any, and record that as the answer to the limit. Let's try the other single side limit. X is heading towards 2 from the left, but that means x is less than 2. So we only care about this region of the graph. Here I needed to put in that solid dot after the fact to keep all of our work parallel since day 1. But as we're getting closer and closer to the input 2 on the x-axis, the output gets closer and closer to 1. So 1 is the result on that limit. Now finally, if it says limit as x tends towards 2, that means we need to be around 2. Values both to the left and to the right matter this time. But here's where we have a bit of a conundrum. Let me put back in that solid dot I accidentally killed off. The values are different when we came in from the left and when we came in from the right. So for this one, we would just say does not exist. DNE being our big shorthand that we looked into. It didn't say to explain why, and there's not a lot of space to explain why, so we wouldn't have to. I'll always look in the instructions verbatim when grading these. But if we did have to explain, we would say does not exist because the left-hand limit is -3, which is not equal to the right-hand limit, which is +1. Or you could say does not exist because there's a jump discontinuity. That's a fair and completely accurate way to answer it as well. Well, any questions so far, folks, with dealing with limit as x tends towards 2, either the double-sided or single-sided ones? Okay, next 3 limits are kind of interesting in a way. Let's do part G first, because we can do these out of order. If we're asked to take the limit as x tends towards -3, we're in this region of the graph. Either side we are of -3, the curve is blowing up. We would interpret a graph like this as communicating to us a vertical asymptote exists. And so this would be positive infinity. And we looked at, say, now part E, part F, they're kind of strange in a way, right? It's now saying if you head towards 3 from the right, if you're on this one, but if you're heading towards the right of 3, you're in this region of the graph. The answer is no different than part G. Here, you're just following that curve, getting higher and higher and higher. This one is also positive infinity. If you look at the limit that says head towards -3 from the left, then that means our eyeballs should be on this part of the graph. around -3, but on the left-hand side of -3. And it's doing the same exact thing. It's just going up towards positive infinity. So we would put infinity on that one as well. So we're nearly through all of them. Going on to the next branch, part H, that's asking us to take the limit as x goes to 0 from the right, from the left, and then 0 altogether. I think H, I, J are a little bit more tricky than E, F, G. They're similar, but different. And that's because the curves seem to be going in different directions as we head towards 0 this time. So let's do these carefully. H is x as we head towards 0 from the right. So that means this part of the curve is relevant. It's going up towards positive infinity, not stopping whatsoever. So this one would be at positive infinity. Next, if it says head towards 0, but from the left, same idea as we used before, we're around 0. But the inputs we consider are all values to the left of 0, and I need to make sure my box captures the actual curve itself. So let me go down below here. There we go, we're around 0, but I want my box to signify where our eyes are looking at to capture the curve. In this region, heading towards 0 from the left, the curve is going down without bound towards negative infinity. So we throw a negative infinity in there for that one. And that means finally, as x tends towards 0 altogether as a statement, that's now a double-side limit. You need to be to the left of 0, you need to be to the right of 0 simultaneously when you analyze this limit. And so we're looking at this overall region. This is a kind of uncomfortable limit. I don't think this situation has occurred at all so far in this class until this one particular problem. There's a lot of nuances to calculus and limits themselves. And so here's the trouble with this. In part H, we said infinity, and it didn't exist, but that was the way it didn't exist. It's blowing up. In part I, we said negative infinity. It also does not exist, but it doesn't exist because of that particular region. It's going down to negative infinity. As we go to 0, this one doesn't exist, but its behavior depends on what side of 0 you are on the very first place. Either it's going to positive infinity or it's going to negative infinity. And so that means the best answer for this one is just a simple does not exist is probably the better answer. The answer the author of the textbook would most likely give. Some people answer this one slightly differently. If you answered it by saying lim x tends towards 0 of f of x is positive or negative infinity, I would say that's not a bad way to think about it either, because now you're conveying it fails to exist because it's either going to one direction, positive infinity, or another direction, negative infinity. And so I would say that is an acceptable answer as well. This would usually be the more typical answer, just an overall does not exist for that one limit there. Again, that's a kind of a brand new limit we haven't seen before. Any question about that one or any of the others? Okay, two more to take a look into. But that's what takes us into the new content, finally. Limits as you go off to infinity. If these exist, that must mean there's a horizontal asymptote somewhere on this graph. And you know, if this was my graph that I made from scratch, I probably would have gone wider on the x-axis just to convey there really is a horizontal asymptote here. So what this author had in mind is, even though the graph was cut off kind of short, there was meant to be a horizontal asymptote at height y equals 0. Likewise, there's meant to be a horizontal asymptote here. It's cut even shorter on the left at height y equals -1. And again, when I produce graphs on real exams, the graphs in the textbook, I think it does a better job of conveying that. It goes off several tick marks to the left to say this blue curve is really approaching that height -1, not just sort of terminating and doing whatever. So using the information that we have, we go off to infinity. We're on this one, horizontal asymptote is y equals 0. We go off to negative infinity, that means we're on the far left, the opposite end. And we're interpreting this to say the curve is getting closer and closer to a height to -1. And so that would be the value of that limit there. And at that stage, we did it, folks. That's the full-on review problem for this one. The next question is going to take us a little bit more than 3 minutes to do. We're not going to try to rip through any of these problems. They're all important. So this will be a good stopping point for us today. Well, any last questions or thoughts at all, folks, before we call it a night? Okay, well, thank you for your hard work, excellent questions, and participation in the class. We're definitely getting through the content. This is week 1 altogether. And if you have any questions, if you're working on Friday, even on the weekend, don't hesitate to email. I check my email every single morning. That's usually when I start grading as well. So I'll always get through all of them. Anything you send, even if you send something late at night, the moment you can think of a question, that's the best time to send out that email. I'll always get to you in the morning. But next week, on week 2, we'll be right back to it in section 2.7 and then launch into defining the derivative. Well, have a great weekend, folks. I'll see you all next week. Thanks. Have a good one.